Okay, I think we'll get started. Today we're going to continue with another lab on the analog to digital converter in the PIC12F675. And we'll come back to talking about some of the important registers associated with that. And in the last lab, if you did that with the 4-bit A to D representation, we just worked with the highest significant bits. Now we're going to actually work with the least significant bits because we're going to develop a coin flip simulator that utilizes the natural randomness of an incoming voltage. So what we're going to do is we're going to just have a free wire, and in fact, just to even improve things, we'll probably hold on to that wire acting as a big antenna, so our voltage is fluctuating quite a bit, and we will read that voltage in with the analog to digital converter, and we will take the least significant bit. So it's very likely that that will be quite random. We aren't going to do some statistical checks on that. Maybe if you want to take this project further, you could actually record the output and see if it behaves in a truly random way. But I think to a good approximation, if it's just grabbing a noise signal, the last or least significant bit should be a random distribution, 50-50 chance of a 1 or a 0. We're going to have, so pin 0 is going to be our analog in. The rest are going to be digital, and we're going to use pin 5 as the input pin, and that will be relayed on a button press. So when we press a button, we will launch the analog to digital converter, pull the signal, and then represent either heads or tails with two outputs here. We're using just a polling method rather than an interrupt here because that's pretty simple, and for this type of thing, there's no need for that interrupt procedure. The polling works just fine. All right, so let's go to the board. Now, we'll go through the program here. Actually, maybe I'll go to the board first. Let's see. So just to kind of narrow in on things, the setup, same as we've always had in terms of connecting to the PIC kit 5. So I'm just using the same breadboard as in all of these videos. Added a button press here and 3 LEDs. The yellow and the green are going to be the heads and tails representation. The red is just going to be indicating that we've pressed the button. So that will just go whenever we press the button. And this isn't working until we get it set up, but the button press is. We can see the red going on, and then the yellow or green will light up whether we're heads or tails. So that's what's going to go on here. So let's go to the code, and we'll start here with just our stuff that's always the same. Actually, all the way down to here is all the same. Little place to put some notes, and then the configuration bits, the include file, where the program goes upon reset or start in terms of the program counter, and so where the main program begins. And then we start our main program, and again, as always, I've got this initial part under main that is the stuff we change just the one time, and then the main loop is what the microcontroller will be doing all the time then after that. So let's walk through this again in case you haven't looked at the other videos. So the status register is where we choose the bank, and the GPIO and the comparator registers are on bank 0, so clearing bit 5 on the status register sets us to bank 0, and that then we can clear the GPIO. We can also clear I could use clear here, but I'm kind of keeping this the same every time, so sometimes we may want to change this number if we're using the comparators. So we're going to just clear the comparator register. Then we will set the 5th bit on status to 1 so that we go to bank 1, because the AND cell, which is the register for the analog to digital setup, is on bank 1. Now let's look on page 44 here. So if you've got your printout there, you can follow along. So we will the last 4 digits, the 4 digits of this binary is setting the analog or digitals. 0 is digital and 1 is analog. So just pin 0 is going to be the analog. The rest are going to be digital I/O pins. Then this bit is of no meaning, and then this bit is setting the clock for the process, and we're just going to use the internal. So that's doesn't have to be a 0, but 0, 1, 1 will be the system clock will be used to set the timing rate of the analog to digital conversion, which takes several steps. Then that is moved to AND cell. So here's where we've written the AND cell. Then finally, we want to load the tris. So again, 1 is an input, 0 is an input, 1 and 2, GP1 and 2 are outputs. GP3 is always an input. GP4 we'll leave that as an output. We won't be using that. And then we're going to set GP5 here as an input. That will allow us to use the button to flip the coin. All right, then we set this back to bank 0 because the GPIO is on bank 0. Now we need some extra stuff for the analog to digital conversion, and what we're doing here, let's look on page 43 of the data sheet. So if you can grab that, follow along there. We go to the analog or the ADC on 0, and then we go to let's look at that here. So this first 0 here tells us we're going to use the configuration where we're right justified. So let's go look at that. It's over here. So we've set a 0, so that means our least significant bit is going to reside in AD-res L bit 6. Okay, so that's what that 0 is doing. We're not going to use a reference voltage. We're just going to use the voltage. So that sets the window, the max and the min for the analog to digital conversion, and we'll just use the VDD or the 5 volts. Then we need to turn we don't want to start. We want to make sure that the analog to digital conversion is off, and that will be this one, and then it's not in process. So that will be, and we don't want to tell it to go. So I'm going to set that to 0. Okay, so that's all the setup, and now let's get to the actual code here. So we're going to pull pin 5 for a button push. So very, very simple. This is how we do a pull. We start this loop, and we're going to skip if set. So normally this is going to be set to 0. So I've got I should have shown this, maybe you can see in here. It's kind of tight, but I've got a pull down resistor here going to ground on pin 5. So it's set at 0 until we press the button, which will set it to 5. And so it will just sit here, and if it's not set, it won't skip this line, and it'll just go back to pull, and it'll keep checking that bit. And then as soon as we press the button, it will skip that, and then it will go into a delay. This is a software-based debouncing delay. So as you press a button, it kind of goes on and off very quickly. And so the first time it sees that it's on, we want to move into a delay because that represents a actual button press, and we don't want to get the on-off effect. Then now this is maybe a precaution that's unnecessary, but because we would just move as soon as we read a 5 volts, we would move into the rest of it. But always good to have kind of a debounce delay in your button whenever you have a button press. Okay, then we're going to turn the the analog to digital off. So we're setting the 0th bit. So that actually, the 0th bit. Let's go back to AD con. So the 0th bit is we're making sure that it's not operating. So we're not. This is kind of a bad descriptor here. We're not actually turning it off. We're just making sure that it's not 1, and it will turn on then when the system starts, which will happen down here when we set the first bit to set it to 1, and then what this will do is start the analog to digital conversion. Now we're going to test for the least significant bit, so we're going to look at the 6th bit in the AD res lower, or AD res L. So that's the least significant bit. If it's clear, we'll skip that. If it's clear, we'll skip that. So that would bring us down to here. If it's clear, then we won't skip this. So it will clear GP2 and set GP1. So that would turn on the yellow light. Now, if it is a 1, so if this is 1, if it's set, then skip if clear. Well, it's not clear, so that will turn on GP2. Skip if clear, it's not clear, so that'll turn on GP1. Skip if set, so it is set. Skip if set, it is set. So that will turn off the yellow light and on the green light. So that'll toggle here depending on heads or tails. Then we have another delay for the loop itself, and I don't exactly know why this is. You have to put some kind of delay in there for the program to work, it seems. It feels like you should just be able to either put a couple of no-ops and then it should work, but for some reason it isn't working for me. Anyway, I wanted a delay here anyway, so there's a short delay here. Then the delay loops, I'm not going to talk about these, but it's sort of it's a 3-layered countdown. So basically, it's 18 cubed clock cycles that it delays for, roughly speaking. If you, in the first video on this playlist, and particularly in the playlist for the PIC12F675, we talk a lot more about the loop, the delay loop. All right, so this is it. So let's go ahead and build this, make sure it builds, write it to the chip. All looks good. So now we will unhook this and hook up the power. Again, whenever I'm working with the analog to digital or the comparator, I like to power the chip on the when we write to it with the PIC12F675, but then I don't like to power that, and you can't even, it doesn't even work if it's connected for the normal operation of the chip. So we're always doing this flip and flopping between the PIC12F675 and then some external source, and this is just plugged right into a USB that's plugged into the wall. So hopefully this is working now, and so what we will see is I will press, maybe I'll go to the just the dock cam, and we will now press the button. I'm going to hold on to this free wire. This is the free wire antenna. I'm going to just have it pinched between my fingers here to add more noise to the system, and then I'll press button, and I think you can see, it's hard to see the red, so now we're yellow, yellow again. Oh, we're still getting a lot of heads. Oh, there's green, yellow, green. Feels like there's a lot of heads and not a lot of tails, but you know, it's so hard with a small number of hits. It's hard to say if that's not really random or random, and so there's the heads or tails. And again, a good way to, I don't think I'm going to do this, although we may actually put a bonus lab in where we're talking to the computer and sending data there. So if we do that, we could check on the nature of the randomness and if it really is a pretty good source of random ones and zeros. But for now, you know, that's something you could do if you're interested in pursuing this further. And otherwise, that's it for this lab.